Okay, let's take a look at a paired t-test example. The problem states a food manufacturer claims that eating its new cereal as a part of a daily diet lowers total blood cholesterol levels. The table shows the total blood cholesterol levels in milligrams per deciliter of blood of 7 patients before eating the cereal and after 1 year of eating the cereal as part of their diets. At alpha equal 0.05, is there enough evidence to support the food manufacturer's claim? Okay, so the first thing you want to recognize for this problem is that we are dealing with a paired t-test because we have the same subject and 2 measurements, and we want to preserve the inherent dependency between the measurements. Okay, so let's go ahead and state the claim in terms of a mathematical statement. Okay, so the claim is that eating its new cereal will lower total blood cholesterol. Okay, so in terms of the mu before and the mu after, okay, we want the mu before, or mu sub b, to be greater than the mu sub after. Okay, so this would be the case that the overall cholesterol level is lowered after eating the cereal for 1 year. Okay, so this is the claim. And this would be the case where cholesterol is lowered. Okay, I'm sure I didn't spell that right. Okay, so because this does not contain the case of equality, this makes this the alternative hypotheses. So this will make the null hypothesis mu sub b less than or equal to mu sub a. Now, one thing the book does is the book writes this in terms of mu sub d, the difference. Okay, so I'm going to go ahead and rewrite this as mu sub d. Okay, so in other words, if I take this mu sub a and subtract it, I would end up with mu sub b minus mu sub a greater than 0. So this is what the book calls that mu sub d. And that's what actually we're testing. Okay, so whether or not the mean difference is greater than 0. So let me go ahead and rewrite the null and the alternative. Okay, so I have mu sub d less than or equal to 0, and the alternative mu sub d greater than 0. Okay, so this is the claim. Okay? All right, so what we want to do is we want to get that standardized test statistic. Okay, so the standardized test statistic formula is our observed mean difference minus the claimed mean difference over S sub d over the square root of n. Okay, so in this section, n is equal to the number of pairs. D bar is the sample mean of the differences. Okay, and S sub d is the standard deviation of the differences. Okay, so we're going to need to get D bar and S sub d from the information. So what I went ahead and did was I put in the information in list 1 and list 2. Okay, so I went to stat, I went to edit, and I put the before measurements in list 1 and the after measurements in list 2. So what I need is a third column of the differences. So I'm going to up arrow and then right arrow to where L3 is highlighted, and then I'm going to press enter, and you'll notice that it puts the cursor down at the bottom of the screen. So what I want to do is literally tell the calculator I want to take list 1. Okay, so that's a second key, a second, and you'll see your lists above the number keys. Okay, so list 1 minus list 2. Okay, so you'll see that list 3 is the column of the differences. So I can do one variable statistics on this third column. Okay, so that's going to give me D bar and S sub D. Okay, so to do that, I'm going to go back to my stat menu, right arrow over to calc, and then select one variable statistics. Now I'm not doing one variable statistics on the first list. I want to do it on that third list of differences. Okay, and then I press calculate. Okay, so it's going to give me the sample mean for that third column. Okay, so D bar is equal to 2.857. Okay, and that sample standard deviation of differences, it's right here. The S sub x is actually S sub d, but the calculator doesn't know that we've named that column a column of differences. Okay, that's going to be about 4.451. Okay, and again, n is equal to 7. We have 7 pairs of data. Okay, so plugging into the standardized test statistic formula, it's going to be 2.857 minus the claim difference. Okay, so let's talk about that for a minute. Okay, the claim difference here is going to be the difference from the hypotheses. So we moved mu sub A over by subtraction, leaving the right side at 0. Okay, so we're actually subtracting 0 here. Okay, and then I want to divide by 4.451 over the square root of 7. Okay, putting that in my calculator, I get a test statistic of about 1.698. Okay, so now I need to go ahead and compare that to a critical value. Okay, looking back at the alternative, this is an upper tail test, and remember the t-distribution is bell-shaped. Okay, so I'm going to shade an area of rejection in the upper tail, and our level of significance for this problem was 0.05. Now the degrees of freedom for a paired t-test is the number of pairs minus 1. So for this particular problem we had 7 pairs of data, so that would be 7 minus 1 is equal to 6. Okay, so I want to go to my t-table and read down to 6 degrees of freedom, and then over to 0.05 in one tail. Okay, so it's the intersection of this row and this column. I get a critical value of 1.943. Okay, so let's go ahead and see where the test statistic is in relation to the critical value. Okay, we see that the test statistic is to the left of the critical value in the non-shaded region. Okay, so essentially we're going to fail to reject the null hypothesis here. Okay, so looking back at our null and our alternative, we are failing to reject the null. Okay, so that means we're keeping the null, and we are not ruling in favor of the alternative. So what this means is that the claim is not supported, and there is not sufficient evidence to claim that the overall cholesterol level is lowered after eating the cereal for a year. Okay? So let's go ahead and get this again using the calculator. Now, there is no built-in paired t-test in the calculator. However, because this reduces to a single t-test by subtraction, I could go ahead and do just a single t-test on that third column. Okay, so essentially the paired t-test reduces by subtraction to a single t-test. Okay, so that's where the notation mu sub d is helpful. Okay, we're testing whether or not mu sub d is greater than 0. Okay, so I already have that column of differences stored in my calculator. So what I can go ahead and do is press Stat, right arrow over to Test, and I want to select option 2, the single t-test. Now I either have the raw data in a column or the summary statistics. At this point I could go either way because I did find the summary statistics here. But I'm just going to go ahead and use the raw data, okay, that column of differences in the third list. Okay, so this mu sub 0 is the value from the hypotheses, okay, and that was 0. And I need to tell it where my list is. I'm testing the column of differences in list 3. And here I can change the sense of direction if I need to. This is an upper tail test, so I want to change that to greater than, and then calculate. Okay, so you'll see that this standardized test statistic is about the same as what we got when we did this by hand. Okay, what the advantage to doing it this way is that we can get our p-value. Okay, so our p-value for this problem is equal to about 0.0702. Okay, so let's go ahead and compare that to our level of significance. Okay, so we have our p-value of 0.0702, and let's compare to alpha, 0.05. Okay, this p-value is greater than our level of significance, and that is consistent with the placement of our test statistic. Remember, the p-value is going to represent the area going this way. Okay, so this area is definitely greater than this area, and we see that once we calculate the p-value. Okay, so this is consistent with our decision to fail to reject the null. Now, if for argument's sake the researcher or the manufacturer was instead using a significance level of 0.1, the decision in that case would be to reject the null. Okay, because here the p-value would be less than or equal to 0.1. Okay, so keep in mind that sometimes the decision changes depending on what level of significance you're using. Now we're going to be sticking with the level of significance that was stated in the problem, but I just wanted to go over again how the p-value compares to the level of significance in general. Okay, so going with the p-value compared to a level of significance of 0.05, the decision is definitely to fail to reject the null hypothesis. So since we failed to reject the null, it's possible a type 2 error may have occurred. It doesn't mean that it did absolutely, it's just that it's a possibility since we're making our decision based on a sample. Okay, so one last thing, I could go ahead and get a corresponding 95% confidence interval for the mean difference. Okay, to do that, I would go to Stat, right arrow over to Test, and then I want the t-interval. So I'm going to scroll down to t-interval. Okay, again, I'm going to go ahead and use my third column of differences and change my level of significance to 0.95. Okay, so notice that our confidence interval limits, okay, from the calculator, the confidence interval blankets 0. Okay, since this confidence interval contains 0, which is the case of equality, okay, case of equality from the null hypothesis, this is consistent with failing to reject the null.